numbers. To solve quadratic equations modulo a power of a prime number, for example, this one. If there is a solution, this solution should satisfy all the same equations modulo a power of 7, which is less than the k. For example, the simplest case, for L equals to 1, there are two solutions, 3 and minus 3. So, without loss of generality, we said x0 plus 3, and now we try to give the solution to z quotient 7 to the 2z. So, trying to give the solutions means that we are looking for an x1 which satisfies those relations as the beginning one, plus that this needs to be equivalent to x0 mod 7. So we do the stuff and we end up to x1 equals 3 plus 1 times 7. If we continue this with the same process, we're going to find x1, x2, x3, x4, as you can see, and go on, which are sums of a number multiplicating a power of 7. We would very much like this series to converge. That means to find the limit of all the xk. So then we would be able to solve all of those equations. But this limit, of course, does not exist in z, so there are no solutions in z. Therefore, in order to put this problem under control, we introduce the p-adic numbers. So the definition of the integer p-adic numbers is the one that you can see, which uses the process we followed to solve the equation. So this range is commutative, addition and multiplication are well defined, and then we define the natural mapping from z to zp. Here there are some examples of how we can compute, how we can represent p-adic numbers, and a natural, an integer and irrational number as p-adic numbers, but we are going to skip that now. And as you can see here, there are many dots. This means that we can keep going indefinitely, and this is possible because of Hensel's lemma, which says that every equation like this that we have seen previously has a unique solution. So let's see one result. 1 is equal to minus 1 mod 2, 1 plus 2 is equal to minus 1 mod 2 to the 2, 1 plus 2 plus 4 is equal to minus 1 mod 2 to the 3, and so on. 1 plus 2 plus 4 plus 2 to the n plus is equal to minus 1, which is true in the field of ZP. Z2, I'm sorry. So until now we have talked about the p-adic integers. Here is the definition of the quotient field of the p-adic integer, which we call the p-adic numbers. Using this theory, we can give an alternative definition which is more helpful. And now we are ready to apply here some analysis, as the title of the conference urges us, because it's analytic number theory. So we define the p-adic evaluation as following, as we can see, and then we are ready to define the p-adic norm. So the p-adic norm is indeed a norm because it satisfies the known properties of a norm. And at last, a very important result of the p-adic numbers is the fact that every Cauchy series in QP converges. I would like to conclude this talk with a very important question, which is the use of the p-adic numbers. First of all, the most popular use were in the proof of Fermat's last theorem by Andrew Wiles, who also proved a conjecture about elliptic curves, which are a special case of the very well-known and very important program in mathematics, the Lagrange program. There are other applications of the p-adic number as well, as you can see here, but I would like to stay more here in physics. There are indeed some applications in classic field theory, particle physics, string theory, and gravitational theory. First is the p-adic Hodge decomposition. This is a generalization of Helmholtz decomposition. This theorem of Helmholtz says that if we take a vector field, we can decompose it. It can be written as a direct sum of a field without curve and a field without divergence. But this, when we try to apply real analysis, does not help us in string theory, because in string theory we find some results who do not satisfy the experiments of the real life. So maybe the p-adic Hodge decomposition can provide us with a solution to this problem. And second, this doesn't have to do with p-adic numbers directly, but it has to do with Zeta-functions, as again the name of the conference urges us, is the Montgomery's pair correlation conjecture. According to Montgomery, the pair correlation between pairs of zeros of the Riemannian zeta-function is the same as the pair correlation function of random Hermitian matrices. The correlation function is a function which shows us different things like the space between different values of the functions. If there are any questions or any contributions to this question, I will be...
It's a goal.
Yeah. So, I would be glad to hear if there are any questions. Otherwise, I would like to thank my supervisor, Panayotis Mertikopoulos, Maria Kulberaki, who helped me with the presentation, and Xenia Spilioti, who invited me to this conference and proposed me to give this talk. Thank you very much.